use of language last class. I said it's the chain rule. It is the chain rule, but it's the chain rule in a sneaky way that you don't usually see. Rewrite the derivative with respect to time as the derivative with respect to position. You can trade a time derivative for a space derivative by multiplying by velocity is basically the theorem there. But that comes paired with an expectation that you re-understand the function of time as a function of space accordingly. Anyway, I shut up. You hit record, right? Okay, I'll begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. Pray you to help us to use this time wisely to glorify you in what we do, Lord. In your name I pray. Amen. All right, so let me get this out of the... So I'll hand the test out, and we'll look at the test towards the end of class. So I don't distract you guys with that. Cover the new material while we're fresh. So there are two techniques. In this class, we have two methods to solve differential equations of the form dy dx equals to f of xy. All right? Two methods. And here, those methods are, number one, separation of variables, and number two, the integrating factor technique. Now, the integrating factor technique is kind of a special, is a specialized weapon. This is really just for solving, just for problems that look like dy dx plus p, which is just a function of x, times y equals to q of x. A little bit off. This kind of differential equation, this is called a first order linear ODE. Now ODE, so in you'll take Math 334, we talk about two different kinds of differential equations. Just as a point of terminology you guys should know, an ODE is an ordinary differential equation. So that's what the O and the D and the E are for. All right. A PDE, in contrast, PDE is a partial differential equation. So what the difference in those terms means, it's just the following. It means that an ordinary differential equation, it just has differentiations with respect to one independent variable assembled from d dx or d dt, but not both. I mean, it's just one or the other. You just have one independent variable and derivatives of those, okay? That forms an ordinary differential equation. In contrast, a partial differential equation has partial derivatives. And what that means, these things you'll learn about next semester, like partial x, partial y, partial t, etc. What that means, though, is that x, y, and t independent. I mean, you can have more than one independent variable. Most of the equations of physics that are important are, in fact, partial differential equations. Maxwell's equations, Schrodinger equation, so like electricity, magnetism, quantum mechanics, all of these at their base are based on partial differential equations. On the other hand, ordinary differential equations are what we typically run up to in classical mechanics, like Newton's second law is what? What's Newton's second law? Oh yeah, so ma is equal to the sum of the forces. Yeah, sum of the forces, right? Now what that means, though, is what's this a? Well, a is actually It's d squared x dt squared, d squared y dt squared, d squared z dt squared. Do you see that? Equals to the net force. So if you actually unravel that, that's a system of ordinary differential equations, in fact, 3 of them, each one of being second order, and usually they're all intertwined. So that's actually quite complicated to solve for interesting forces directly, but that's physics, all right? Physics is solving that differential equation, classical mechanics. All right, enough, what's the word? This is liberal arts. I mean, this is I'm just giving you breadth at the moment. I won't really test on that. There's no reasonable test question I can ask you about that material, but I think terminology is important for you to be aware of, given your respective majors. So let's get back to the task at hand. Let's talk about how to solve problems like that. All right. So my example 1 today will be a pretty popular one. What if we have dp dt equals to, let's say, kp? What's this? So here we're thinking of p being population, all right, and k is the growth rate. What this says is that the change in population with respect to time is proportional to the population that's there. This is so-called exponential growth, right? I mean, so it's population. Now, population of what? Whatever you want. If you can find something that obeys this really, really simple rule of population growth, then this is your model. It's most effective for things like, say, bacteria in a petri dish over small time scales. Right? Not so good for populations of nations over millennia. All right. Anyway, we can solve this. Here, k is a constant. So what have we got? Let's separate and integrate. Excuse me. So we got dp over p equals to k dt. Excuse me. So we separate variables, and then we integrate. Right? So integrate. So on the one hand, I get natural log the absolute value of p. And on the other side, I get kt plus, say, a constant. Probably we want to solve for p, right? So the absolute value of p is equal to e to the kt plus c, which gives me that p is plus or minus e to the c times e to the kt. It's kind of the same algebra we did yesterday. We had an x cubed up there, but it's more or less the same kind of. What's that? P can't be negative, right? Yeah, but p can't be. Yeah, right, it's population, so I don't know what would be negative population mean. I don't know. What's that? Murder spree. A murderer. Like the person, someone with the potential to take lives. That would be negative. He'd have negative population. Interesting. Huh. That would be fun to pursue. Anyway, but yes, oh wait, not what, let's not take that out of context here. Let's say, so p of 0, let's say is the initial population, right? P of 0 is p0, but that's also going to be equal to, so let's just say that this can be rewritten as like c bar times e to the kt, right? So this would be c bar times e to the 0. But e to the 0 is 1, so we learn that this c bar, the constant we're looking for, is actually just the initial population. So therefore, population at time t is just equal to the initial population times e to the kt. There you go. This is the so-called exponential population growth. It is simple to derive with separation of variables. Right. Do you guys know how to rewrite this in terms of doubling time? Do you know what doubling time is? A lot of times when we talk about this application in biology or something else, we don't talk about it in terms of this formula. We might talk about it in terms of a half-life or a doubling time. Here, let me look at it a different way. Here, almost the same math, example 2. You might have dn dt equals to minus, say, 10n. Here, n would be the number of particles, and minus because I'm thinking of radioactive decay. So this would be something like radioactive decay. Radioactive decay, you know, that's why it's negative, and n is the number of particles. Usually I say n, you can think of the number of particles like polonium, and then like, you know, think about it decaying in your fridge or something. The half-life's like 3 months, or depending on the brand, I don't know. But anyway, radioactive decay. So I mean, it could be something else. Like it could be the number of neutrons. Neutrons have a half-life something like 11 minutes. Okay. So if I have 20 neutrons just sitting out by themselves, by their lonesome, then after about 11 minutes, you'll have 10 of them. They decay into protons and electrons and some other things. Anyway, you guys have heard of radioactive decay, right? You're aware. Anyway, so that's the differential equation. It simply says that the number of particles, the number of particles present determines the change in that number. It's proportional, again, to the number of particles present. And it's a completely random process. That's what radioactive decay is. So this differential equation models that. And so the same math, right? The same math gets us to what? It gets us to n of t is equal to the initial number times e to the minus 10t, right? So if you wanted to rewrite this in terms of, say, half-life, what would the half-life be? Let's say half-life, let's use tau for half-life. How about that? Has what? N of tau should be equal to what? If I start with what's, yeah, and n sub 0 divided by 2, right? The initial number of particles has been halved. That's half-life. So if you work that out, we have n sub 0 over 2, right, is equal to n sub 0 times e to the minus 10 tau. So the n sub 0's cancel, right? And we get 1/2 equals e to the minus 10 tau. We want to solve for tau. How do we do that? Yeah, take the log of both sides, like that. Natural log of 1/2 is the natural log of e to the minus 10 tau, also known as minus 10 tau. So what's tau? It's minus 1 over 10, the natural log of 1/2. Can we simplify that? Let's see here. The natural log of 2 to the 1/10th power?
No. Oh, I see. Yes, that's.
Yeah. Is what you said. No. What you said was half right, so it's good. But, yeah. Now, so if you go back and put that in, what does that give us? So anyway, there's the half-life. It's the natural log of 2 to the 1/10th power. Whatever that would be, right? Now, of course, this is depending on what units we're using for time. If time is in seconds, then that's natural log of 2 to the 1 over 10th seconds. If the time happens to be in, you know, pick your other favorite unit of time, minutes, light years, light seconds. Well, light years. But light years unit distance. So my question to you guys would be, can you rewrite the formula in terms of, let's see here, how can I say this? Can we re-express n of t, n naught e to the minus t, 10t, right? if we rewrote this as n naught times 1/2 to some power, let's call it Pac-Man. What should Pac-Man be? And can I do that? He said his first answer was no. So of course the correct answer is yes. Right. So we cancel the n naughts, right? And then we get e to the 10t is equal to 1/2 to the Pac-Man. So how do you solve for Pac-Man?
We want minus 10t though,
Oh yes, thank you. Yeah, take the log of both sides. So log of both sides gives me minus 10t equals the natural log of 1/2 to the Pac-Man, right? Which is Pac-Man to the natural log of 1/2. So that gives me that 10t equals to, oh, I'm sorry. Oh, I'm so sorry, guys. It's fine. It's fine. It's just not the Pac-Man I had in mind. Pac-Man minus good grief. Pac-Man log 2. I mean, this is minus the natural log of 2 times Pac-Man, right? So the minuses cancel, is my point. And you can solve for Pac-Man. What's Pac-Man? 10t divided by what? Natural log of 2. So let's see here. What do we get? N of t we can write as n naught times 1/2 to the what? 10t over natural log of 2, right? But let me suggest to you we could also write that as n naught times 1/2 to the what? Oh, and I'm sorry, I had set up the camera so that it was for the projector screen at the start. I think I've been zoomed out too much, and you know, these YouTube commenters are very vicious. I don't want you to read them later and see I'm way too far out. Way too far out. There we go. There we go. So guys, if you look at the last thing we got to, look at the last thing we got to there. And can you see it? Okay. Can you tell me how to rewrite the last formula we got in terms of tau? What was tau? Oh, man. Yeah, I think this is more fun if we write this natural log of 2 divided by 10. Oh, that's what you said? Oh, sorry. Yeah, the natural log of 2 to the 1/10 power. I mean, it's not wrong, but it's just also weird. But look at this. This is what? This is actually t over tau. So anyway, just to takeaway message here, we can also write n of t is equal to n naught times 1/2 to the time divided by the half-life. Now, we had that the half-life was what? It was the natural log of 2 divided by what? Divided by 10. If you replace the 10 with k, what would happen? If we had dn dt equals minus kn, then that would just put a k here. So anyway, maybe you might run into these in like a chemistry class or something, yeah? All right, I think I'm getting too far into the application here. Let me go to my next example. What if we had dp dt equal to kp, all right? You're like, well, that's what we already had, right? It's getting worse with it's getting worse. But then you take this and you multiply this by 1 minus p over c. All right? That is true. It's all about center mass. So what would this is also a model of population growth, all right? And it's, if p is small, right? Let's talk about this model. There's two very kind of limiting cases here, right? If p is approximately 0, then we get dp dt equals to what? Just kp, right? Because the second term, I'm assuming c is relatively big, okay? So p over c is pretty small if p is approximately 0, and the dominant term would be just kp times 1, right? On the other hand, another special case, what if the population is approximately c? Right. Then p over c is like 1, right? And 1 minus 1 is 0. And so dp dt is approximately 0, right? So the idea of this model is that as the population gets close to c, which is called the carrying capacity, the population growth slows to 0. Right? So you can see that if p is greater than c, then dp dt is what? It's actually less than 0. Can you see that? If p is greater than c, that makes this factor larger than 1. And then we have 1 minus something larger than 1. P is population, so it's positive. Right? And then, then the dp dt will be negative. So the population will decrease if the population is larger than the carrying capacity. On the other hand, if the population is less than the carrying capacity, then what? Yeah. Is greater than 0, because we're taking 1 minus something positive. Understand that k is a positive k is assumed to be positive here. K and c are both positive in my model. P, of course, is also, for physical reasons, positive. There's another special case, right? If the population was exactly equal to c, what would happen? Well, dp dt would be 0. What does it mean if the derivative is 0? No change, right? That'd be constant population. So if you could somehow hit the carrying capacity, you just stay there according to this model. So this model somehow has incorporated both a birth rate and a death rate. Really, if you multiply this out, right? If you multiply this out, you get kp minus k over c p squared, right? So this is birth rate, death, right? That's roughly the idea. Okay, so can we solve this? How do we solve it? Tell you what, let me set k and c both equal to 1, so math less annoying. Okay? Don't worry, on the final I'll put them back as variables. Oh, it's too soon. It's too soon. Hey, I don't want to grade that either. In my notes, when I get my computer out, I'll show you where these are. I have actually solved it with the variables there. But anyway, so here we go. we're trying to solve dp dt equals to p times 1 minus p. So what do we face? We face the problem of dp over p times 1 minus p equals to dt. And just to be less weird, I'm going to shift a minus from the left-hand side to the right-hand side. So this gives me the same as dp over p times p minus 1 equals to dt minus dt. And I just prefer to do that because I know where we're going, which is partial fractions. And so how do we integrate then? Well, I'll do the right-hand side that for free. That's minus t plus a constant. See? I'm so nice. I did that for you guys. On the other hand, the other side, well, we got to do this integral, right? Right? So here's what we're going to do. We're going to 1 over p times p minus 1 equals, what's the partial fractions decomposition here? A over p, yeah. Plus what? B, yeah, b over p minus, that's it, right there. That's partial fractions decomposition. Now we need to figure out what a and b are. How do we do that? Multiply both sides by the denominator. And then I would suggest we plug in population 0, population 1. See what happens to us. P equals 0 gives me 1 equals to, looks like minus a. And p equals to 1 gives me 1 equals to b. So therefore a is minus 1 and b is 1. So going back to my integral, this is actually the integral of, I'll put the b term first because that's more sort of natural for me. 1 over p minus 1 minus 1 over p dp. Now that I can integrate, right? So that gives me the natural log of the absolute value of p minus 1 minus the natural log of the absolute value of p. What did I do there? I made a u equals p minus 1 substitution there, right? That was a substitution I made in my brain. But now it's on the board. Oh no, my brain is on the board. Such violence. So, properties of logarithms. This is natural log the absolute value, p minus 1 over p. Actually, properties of both logarithms and absolute value I just used there. I used a property we know for absolute value, which is that the absolute value of alpha over the absolute value of beta is equal to the absolute value of alpha over beta. Fun fact. It's true. And so now I'll exponentiate both sides. And so I get p minus 1 over p, absolute value, is equal to e to the minus t plus c, which again is e to the c times e to the minus t. Right? And so what that gives me is that p minus 1 over p is equal to some constant. Did I use k yet? I guess I should use some. I mean, I don't want to think. I'm not trying to tell you the same k as at the start of all this. I need some other constant. J? All right, J. Yeah, J is a good constant. I like that, J. J e to the minus t. Now I'm trying to solve for p. Can you solve for p? This says p minus 1 is equal to j p e to the minus t, which says that p minus jp e to the minus t is equal to 1, which says that p times 1 minus j e to the minus t is equal to 1, which finally says P of t is equal to 1 over 1 minus j e to the minus t. There you go. And j depends on a somewhat complicated way. I mean, the initial population, as it relates to j, it's somewhat somewhat complicated. But anyway, there it is. Let's see here. What if we were to solve dy dx equal to, how about x cosine of x squared times the cosine of y? So this is a separation of variables problem. I think I think we can separate variables. What would separation of variables give us? It gives us dy over cosine y, right? Equals x cosine of x squared dx. So we separate variables. Now we integrate both sides. Oh, left-hand side, a blast from the past, right? This is secant of y dy. And on the other hand, that's the integral of what? That's cosine of u times du over 2, right? Let u equals x squared, so du is 2x dx. So x dx is equal to du over 2. Now secant y, maybe you remember, this integrates to give us natural log, the absolute value of secant y plus tangent y, and that's going to be equal to 1/2. Oh, I can't do math. What's the integral cosine? Sine, yeah. 1/2 sine of, well, I guess I can put u back. You guys will follow me. Sine of x squared plus a constant. There you go. That is the answer. I hope you guys, I've spent some time talking about applications in here because I wanted you to appreciate how, connected differential equations are to applications, but you shouldn't confuse that for what I'm actually going to test you on, which is mostly like this, right? So basically these problems are just two integrals packed into one. Yeah. So like the penultimate separation of variables problem involves trig substitution and partial fractions in the same problem. No? I'm more excited about this than you guys. Okay, fine. But anyway, does that make sense? Now, can you solve for y? I cannot. I'll just tell you, I cannot solve for y. If you ask me to solve for y here, I can't do it. So at best, I could locally approximate y as a function of x. There are tools for that in advanced calculus. Or even regular calculus, you kind of already know how to do it. But anyway. One more example, then we'll turn the page to the next technique. Example 5. Suppose we wanted to solve dy dx equal to e to the x plus y. Now I will sometimes ask this in differential equations, usually the first test. And I usually get about, I don't know, a third of the students, they're just lost. And the reason they're lost, I think, is because they didn't know that you can do this. But you guys know that, right? So now we can separate variables. That gives us dy over e to the y equals to e to the x dx. Or, better yet, this is e to the minus y dy equals to e to the x dx, right? So we separate, now we integrate. Integration gives me minus e to the minus y equals e to the x plus a constant. Where's that minus from? That's from a u equals minus y substitution, if you like, but I don't think you need to write that down. If you can, I mean, we should all agree on that. And now I can solve for y here. This is going to give me, now, is it okay to take the natural log of this equation, by the way? It is not, right? Because it's negative. Minus e to the minus y, that is minus e to the something is a negative quantity. Natural log of that does not make sense. Unless you're in complex variables. So here, sorry, I'll behave. E to the minus y is equal to, minus e to the x minus c. Or to be more kind of, just to make you feel better about it, c bar minus e to the x is really the way to look at that. The point is c bar is positive, and that compensates the minus e to the x such that the total quantity here is positive, and we can take the log of it, right? So apparently that c that I wrote at the start has to be a negative constant. Anyway, if there are going to be any x and y that satisfy this. So then we take the natural log of both sides. I get minus y equals to the natural log of c bar minus e to the x. And then solve for y. So y is equal to, minus the natural log of c bar minus e to the x. There you go. That is the explicit solution to this problem. You guys starting to get the hang of it? Maybe? All right. All right, so I think a lot of you, I think most people could do separation of variables without a lot of guidance. All right, I think it would be something maybe some of you would even try on your own, just if you thought about these things long enough. In contrast, what I'm about to show you is unexpected. There are ways of motivating it, but none of those are particularly relevant to this class. And so I think it's better to show you how it works rather than just motivating it. So what I'm going to do, guys, is I'm on the one hand here going to look at dy dx plus py equals to q. Here, p and q are given functions of x alone, okay? And so what I'm going to do here is, on the one hand, I'm going to work the theoretical, and on right next to it, I'm actually going to work a problem for us to illustrate each step in the derivation as we go. All right? And you'll forgive me, but I will fill in this blank in a second. I need to think about it. Okay, so actually the first step in this actually is making sure that the differential equation is in this format. This is called standard form, right? So this is the standard form of a first order differential equation. Basically, we got to solve so that dy dx and y are on the same side, and that the dy dx has a coefficient of 1, all right? So that we got that. Step number 2, or step number 1 really, is to, we said I is equal to the exponential of the integral of p dx. All right. This is called the integrating factor. So over here, we're going to say I is equal to the exponential of the integral of minus 2 dx over x. What is that equal to? That's minus 2 natural log the absolute value of x for that function, right? And then by properties of logs, that's e to the natural log of the absolute value of x to the minus 2, which, by the way, is just the absolute value of x to the minus 2, which, by the way, is 1 over x squared. Now, obviously, I can't compute the integral of the abstract function p in general, but I can just leave it like that. So step 2, I'll make here, is to notice what's di dx equal to. Well, that's equal to d dx of what? Of e to the integral of p dx. So if you do this abstract differentiation, what do you get? Well, you get e to the integral of p dx times d dx of the integral of p dx. Well, what's the derivative of the integral? I mean, here it's an antiderivative, actually, right? What's the derivative of an antiderivative? Well, it's the thing we're anti-differentiating. It's just p again. So you'll notice that this is I, and that is p. So what we got is that di dx is ip. And that is also true over here. You can check that di dx is what for us here? It's equal to what was my p? Oh, it's minus 2 over x. It's minus 2 over x times I. That's also true here. I should say I times p. Sorry. I did pi. So what is I? I here was 1 over x squared. What's my p? My p was minus 2 over x, right? And so that gives me minus 2 over x cubed, which is, in fact, yes, what we get from differentiating that, right? I'm showing you it works. All right, step number 3. And honestly, step number 2, you don't really do for problems. Like, I don't technically, step number 2 is not really needed for the actual problems, but it is for the derivation. 3, multiply by I, the differential equation. Whoa, this marker. Wow. Yowzers. That was stout. So we have I dy dx plus IP y equals to IQ. So for the problem we're looking at, we have 1 over x squared dy dx minus 2x, minus 2 over x cubed y is equal to, all right, just a second, I gotta think about this. I meant to put an x squared sine x here. There we go. All right, so we have x. So we have 1 over x squared times x squared sine x, otherwise known as sine x, right? All right, guys. So who can tell me why we multiply? I mean, what's the point of multiplying by the integrating factor? What is it? Can you tell me on either side of this how we can simplify what we're looking at? I mean, what is this? D dx of what? I'll give you a hint. There's a y in here. Y times what? So over here, how about this? I times y. See, because this IP is what? It's really di dx, right? So you're looking at I dy dx plus di dx times y. That's the derivative of I times y with respect to x by the product rule. So this is product rule. I said product root. I don't know what that is. Product rule. Over here, it's 1 over x squared times y, right? 1 over x squared times y, differentiate it, you get 1 over x squared times y dx minus 2 over x cubed times y. That's the product rule. What you're seeing going on the left-hand side is evidence that this is not an accident for my example. It's an inevitability. The integrating factor forces the reverse product rule to work. Now that we have reached that point, then we can just integrate both sides. Once we have a derivative of something equals something else, we can just integrate both sides to solve that. So step 4 is just that I times y is equal to the integral of IQ. So therefore, y is 1 over I times the integral of IQ. And that is pretty much a general formula which will solve this. Right? And then over here, for this problem, I get 1 over x squared y is equal to the integral of sine x dx. What's the integral of sine x dx? Yeah, minus cosine of x plus c. Important to add the c here. And now we can solve for y. So y is equal to x squared times c minus cosine x. There you go. That's the solution to that problem. So this is the technique. Integrating factor technique. Step number 1. I'm going to renumber it if you don't mind. To keep the numbering the same, I'll start at 0. 0. Place differential equation in format dy dx plus py equals to q, if possible, of course. Step number 1, calculate the integrating factor I equal to the exponential of the integral of p dx. Be careful, if there's a minus, you need to be careful to include that in your p. If you neglect the minus, you will be wrong. Step number 2. Actually, step number 3 is next. Okay. Step number 3, multiply star by I. Step number 4, reverse product rule. You'll have d dx of IP equals to IQ if you did step 1 correctly. There's a redundancy here. If you calculate the integrating factor wrong, then the reverse product rule won't happen for you. So if you should think through the reverse product rule. If you do, this is a self-correcting method. And then step number 5 is just that the integral of d dx of I p dx is equal to the integral of IQ dx, right? Which tells us that iy tells us the integral of iy is equal to the integral of IQ dx. So solve for y. And be careful to add c in the process of the calculation and not at the end. We do not just wait till the end of the problem to add the constant. You got to add the constant when we do the integration, right? We add the constant here, not after I've solved for y. You have to add the constant, then solve for y, because the constant gets all intermixed with the formula. It's not usually additive. This is the integrating factor technique. Do you guys think you can learn it? I hope so, because you have a quiz on it now. So here's your quiz. Actually, I probably should put it over here. Let's solve dy dx minus 3y equals to e to the x. All right? I would like for you to find an explicit solution to that problem, right? If you do it correctly, it's worth 10 points. I'll give you some help with it. So let's just talk about this together. What's the P and what's the Q here? P is minus 3. My Q is e to the x. Do you really do anything with the Q? Not really. Not until the end, you know. So if P is minus 3, what's the integrating factor? I'll let you guys work it out, but just follow the steps, okay? By the way, these are bonus points in the sense that you've already got 1,000 points from everything else, so these just add. You really can't go wrong if you do something here. I'm just trying to give you some incentive to really think through it for yourself today. So do not be distracted by these silly tests until after we're done with this quiz, all right? I'm just handing them out because... All right. Everyone should have found I by now. What did you find for I? Negative 3x. E to the negative 3x, right? E to the negative 3x. So what's the next thing we do? So what's that get? E to the minus 3x. Okay. 3e to the minus 3x times y, right? Right? Now how does e to the minus 3x times e to the x simplify? E to the minus 2x, yeah. Grant. Jeffrey. There you go. Give you yours. Mm-hmm. Wait a minute. Did I think I just gave you the wrong one. I knew it was wrong as soon as I did it. Let's see here. Does everybody who's here have a test from me? Who's missing? You're missing it. Brandon? Yeah. There you go. So James and Jesse are not here. Wait a minute, no. Wait a minute, what did I give you?
Grant.
Ah. See, I said Grant. You looked up. I thought you were saying you're Grant. Sorry about that. So does the reverse product rule work? What we got? Did it work? What was this, ddx or what? Derivative of what gives me what's above? Uh-huh. What's your question, Josh?
Is the reverse product rule d dx ip equals iq itself, or is it you're supposed to...
I really just mean by the product rule, but we're doing it in the opposite way we're used to. I mean, if I differentiate this product, right?
Yeah.
Do I get that? I get derivative of that is minus 3 to the minus 3x, that term.
Yeah, but that's... So you're not reversing the product rule.
Well, we went from here to here. My point is usually the product rule starts with FG, right? And then we go, or whatever. But we're starting over here and we're going over to there. And that's, in that sense, it's reverse. Yeah? But in another sense, the product rule is inequality. So you can really talk about whether it's forward or backwards. I mean, it's an identity between derivatives and the product of derivative of the product. So, yeah.
Is it y equals e to the x plus 3?
Let's see here. So you're going to integrate. What happens when we integrate this? We get e to the minus 3xy. What's the integral of e to the minus 2x? I'm working myself into a corner. Yeah, minus 1/2. Yeah, e to the minus 2x, right? And I got to add a constant here.